Hi everyone. Today I would like to talk about least square. Least square is the most widely used estimation technique for machine learning and signal processing. So it's very important to have a good grasp on least square concept. Why do we use it? When do we use it? And how to actually solve least square problem. It has numerous applications in other domains as well. It's actually the first estimation technique that usually people try. Okay, so let's start. Assume you have a matrix A that is m by n. So it has m rows and n columns. And also m is greater than n. So we have overdetermined system of equation. If we have a system of equation, or we have a tall matrix. Okay. So for example, A can be like this form. It's the tall matrix, right? So m is greater than n. Here is n. Here is m. M is greater than n. Now we talk about this. Um, Actually this system of equation where A is a tall, AX equal to B, we call this one overdetermined system of equation. Overdetermined. We have more equation than unknown. Okay, so here we either have a unique solution or we don't have any solution at all. Under what case we have unique solution, or under what case we have no solution? If you write A based on is columns. Again, remind you an, we have n columns. We said that when you're multiplying matrix vector product, the column representation, it would be the best representation. So you can write AX as a linear combination of column of A, x1, A1 plus x2, A2, all the way to xn, an. Okay, good. The same thing I have here. So now if B can be spanned by columns of A, then we say that we have a unique solution. This means that if we have some x1, x2 that satisfies this star equation, then we have a unique solution. If not, means that if B is not a linear combination of columns of A, then we don't have any solution. Okay, good. Now assume we don't have any solution. Assume the second case is correct, meaning that B is not a linear combination of column of A. Therefore, we know that AX equal to B has no solution. But what if I'm not looking for X that exactly satisfies this AX equal to B? What if I want to find the X that minimizes the distance between AX and B in m-dimensional space? Okay, so if we had AX, if this is a scalar, and this is a scalar, let's see, right? And then we had some sort of B, which is a scalar. If we had these scalars and we wanted to minimize the distance, our objective function would be, for example, absolute value of AX minus B, a square, because taking derivative eventually from the square is easier. Or we don't need this absolute value in a case of a square, actually. So we would write AX minus B square, right? If they are a scalar. Now this square doesn't make really sense when we have vectors, right? Because A times X, you have an m-dimensional vector, and B also is m-dimensional vector. So we have to come up with another notion to measure the distance between these two vectors. And that's where we use the norm, L2 norm, for example. We can use other norm, but here for this square, we mainly define L2 norms, okay? So our goal in this square is that when AX equal to B has no solution, we want to minimize the distance between AX and B, or we want to minimize the norm or the norm square of AX and B. So this is our objective function. This is the equation I could represent double star. Find the X such that it minimizes the norm square of AX minus B. Okay, so least square used a lot in data fitting. Actually, the function polyfit and polyval, for example, in MATLAB, they implement the least square for the polynomial curve fitting. Okay, if you use that one for this polynomial curve fitting, then sometimes you call it also regression, which means that you're regressing the vector B on the columns of A. Okay, which is used a lot in the literature. You have algebra linear regression, for example. That's what the solution of linear regression is usually found by least square when the noise is normally distributed. Okay, good. Now let's talk about a little bit about the interpretation of the least square. Again, we have two interpretations, column interpretation and the row interpretation. Let's look at the column interpretation. Column interpretation of least square means that you want to calculate the norm square of ax minus b, this one, this quantity, right? But wait, I said ax can be written as a linear combination of column of a. So that's what this expression represents, minus b, norm square, right? So what are we looking for in this case? We are looking for linear combination of column of a that is closest to the vector b, right? So that's what this one says. So when you write min of ax minus b square for the x, means that we are trying to minimize we are trying to find the x and minimize this quantity in the column interpretation, which means that we are trying to find a linear combination of column of a that is closest to the vector b. Okay. By the way, this, when you write this minimum value, this expression here is called the objective function, right? Or cost function or loss function, right? So this, sometimes you want to maximize that, sometimes you want to minimize that. Okay, good. Now let's take a look at row interpretation. Row interpretation might be more useful actually. So here during the row interpretation, assume I have this A. Instead of looking at the columns of A, I look at the rows of A. A is m by n. So how many rows do we have? We have m rows, right? We're going to represent rows of A by A1 transpose, A2 transpose, all the way to AM transpose. These are rows of A. Now, when you do AX minus B, let's see what exactly you get. So when you write AX minus B, this is what you get. You will get the way the non-matrix vector product work is this. You're going to go ahead and multiply the first row of A by X. So you get A1 transpose X. This will give you what? This will give you the first entry, right? You have to subtract it from B1, the first entry, right? So this B is going to be this B1, B2, all the way to BM, right? What's going to be the second one? Second one is going to be A2X minus B2, all the way to AM transpose X minus BM, right? So now I said here, let's say that each of this AI transpose X minus BI is going to be RI. RI is for residual, right? So each of these, for example, this one is going to be R1. This one is going to be R2. This one is going to be Rm, right? So then what would be the norm square of R, right? So it's going to be what? It's going to be the norm square of AX minus B, right? What would be? It's going to be the Euclidean norm. What's the Euclidean norm of this vector A, for example? If you have, let's say, I define this vector M. It's going to be M1, M2, all the way to, let's say, Mn. What would be the norm square of this M? It's going to be nothing but sigma I from 1 to n mi square, right? You have sum of a square of the element of the vector. The same thing is here. So norm of ax minus b square is nothing but the square of the first entry plus square of the second entry, all the way plus the square of the last entry. And that's what I have here. Okay, good. Now, minimizing this norm of the residual square, or ax minus b square, is like minimizing the sum of m residuals, right? This is the first residual R1, this is the second residual R2, and this is the last residual Rm, right? So now I said here corresponding to M linear equation. What do I mean by that? So what is this A1 transpose X B minus B1? So what is A1 transpose X? So A1 transpose X. Let's take a look at that. A1 transpose is the first row of A, right? So this is going to be the dot product of the first row of A and then vector X. It's going to be what? It's going to be A11 times X1 plus A12 times X2 all the way to A1M times XM, or A1 N column, right? Then this is going to be minus B1. This is one system of equation, right? You can write it, for example, this one as this equation, system of equation. This is corresponding to what system of equation? A1 transpose X equal to B1. What about the other one? The other one you're going to write as the second row now. A21 X1 plus A22 X2 all the way to A2N Xn equal to B2. And then we have AM1 X1 plus AM2 X2 all the way to AMN Xn equal to Bm. Right? So that's what I've written here. Minimizing norm of R squared is like minimizing sum of M residuals corresponding to M linear equation, right? So what does it mean intuitively? So let's say that, for example, you might say that I can find the X here such that it satisfies the first row, this one. This is the first equation. But wait, so this makes this residual R1 equal to 0, right? But it doesn't make R2 or Rm equal to 0. So let's say if you calculate the norm of R squared, you get 10 using this. And now if you find the X such that it makes the second row equal to 0, it makes R2 0, but it doesn't necessarily make R1 or R3 or Rm equal to 0. So this is going to be 12, right? And then so on and so forth. You are looking for X that minimizes the sum of this expression. R1 squared plus R2 squared all the way to Rm squared, right? Or make them as small as possible. So remember this row interpretation is more useful than the column interpretation for the context of least square. Okay. Now let's talk about the solution of least square problem, which is a very important problem in literature. So there are two ways to look at this. One of them is that when you write it component-wise, or when you write it as a matrix vector product. Let's first take a look at that when you write it component-wise, meaning that we write the A in terms of the row interpretation, and then we try to expand that and then take a derivative. Let's see how it works. So the objective is J, usually it's denoted by J, is to minimize this norm of AX minus B squared. You can write it like this. This is exactly what I have written here, right? So this AI is corresponding to ith row of A minus BI squared, right? Sum of corresponding to sum of M residual square, okay? Now, if you go ahead and take a derivative with respect to X, what would we get? Let's see. So this one is as a square. You're going to have 2 AI transpose X minus BI, right? Then, of course, we have a sigma here from 1 to M, but then wait. These quantities, each one is a scalar, right? We need to know also that using chain rule, what's the derivative of this term with respect to X? What would be that? It would be AI, right? It doesn't matter whether you write the AI actually here or you write the AI here. For this problem, it doesn't really matter because AI transpose X minus BI is actually a scalar. Right, so you're multiplying, it's like 2 or 3. You're multiplying, you can multiply anyhow you like by the vector. So we are gonna write this 2AI. So, and that's why I have this expression. We set it equal to 0. You're gonna go ahead and divide this one by 2, this expression. So you will have this. This is called also normal equation, but usually the normal equation you see in the literature would be based on when you write it based on matrix vector product, right? So what you're gonna get here is this. You're gonna get sigma I from 1 to M, AI transpose X is equal to sigma I from 1 to N, AI BI, okay? And from here, X is equal to this expression. That's definitely valid expression, and it's definitely satisfactory. Okay. But usually what you see in the literature and what is really common is to write this 3-star equation as follows. This one, like this 4-star equation. This 4-star equation is called normal equation. And from here, x is equal to A transpose A inverse A transpose B. But this one, this one is exactly what we have this. This is all the same. This is a matrix vector version, and this is a componentized version. Okay. Now, this is what you see a lot in the literature. But then wait, I want to remind you something. Recall, what was the pseudo inverse of left invertible matrix? So we know A is a tall matrix, M is greater than N. What was the pseudo inverse in that case? The pseudo inverse that we denoted like this was A transpose A inverse times A transpose. But isn't that this? So again, just remind you something. When AX is equal to B and A is a left invertible matrix, what we do is that we multiply it from the left side by the pseudo inverse, and we get X is equal to A pseudo inverse B, right? So the X would be equal to what? A transpose A inverse A transpose B, right? So what this means is that if AX equal to B has a solution, that's what I wrote here, then X hat is equal to A pseudo inverse B, which is the solution of AX equal to B, right? And if AX equal to B has no solution, then X hat equal to A pseudo inverse B is a least square solution for the problem AX equal to B. So when you go to the MATLAB and you use this backslash operator, this actually implements the least square problem for you. Whether it has a solution or not, MATLAB doesn't care. It always uses the least square operation, right? So this pseudo inverse is gonna be a pseudo inverse B is gonna be a solution to the least square problem. Okay, so anytime you give them matrix AX equal to B, MATLAB will, or Python will implement the, or any program language of your choice will implement the least square problem. And this is why it's actually very common, least square. It's used every time in a system of linear equation. Okay, so remember this pseudo inverse that defined a couple of videos ago for a left invertible matrix is used also in normal equation, and it's giving us a solution the same X hat. Okay, so the least square solution is a solution of AX equal to B. Now, what is method 2? Method 2 is that we don't write it component-wise based on row interpretation or column interpretation. You just go ahead and use the definition of the norm, simplify, take a derivative with respect to x, and then find the answer directly. This is very common, and it's very important to know how to use this method. We want to find the minimum ax minus b. What I'm going to do, I'm going to recall you that the norm of r squared, not this, norm of r squared is going to be what? R transpose r, Euclidean norm. So that's what I do here in this step. Then what I'm going to do, I'm going to use the property of transpose, that AB transpose is equal to B transpose A transpose, and A minus B transpose is going to be A transpose minus B transpose. These are the properties that I've used. So I transpose the first parenthesis. That's what I get. Then I multiply them together. This is what you get here. Now you're going to go ahead and take it with respect to x. Couple of notes. Note one. If you have x transpose bx, if this is your j, if the j is this, then round of j, round of x is gonna be what? It's gonna be b transpose plus bx. You can derive this up. The second one is that if you have j is equal to a transpose x, where a is a vector and x is a vector, then round of j, round of x is gonna be a. Okay, so now remember here we get b transpose b. But if B transpose is equal to B, means that B is symmetric, then we get 2B. So here, this A transpose A is a symmetric matrix. A transpose, a ground matrix, is symmetric, is equal to A transpose A, symmetric matrix. So what we get after we take a derivative with respect to X for this expression, we get A transpose A plus A transpose A. Now, X is a vector, A is a matrix, B is a vector. This is going to be a vector. This by this is going to be a scalar. This is a scalar. This is going to be a scalar as well. One of them is transpose of the other. 4 transpose is 4, right? So you can write this one and this one together to be negative 2B transpose AX, right? Plus B transpose B. These two together is going to become this. Now you take it with respect to X, you get A transpose A plus A transpose A times X. Recall, this multiplied by this is a vector. Consider this multiplied by this to be A transpose. Come here, A transpose X. When you take it with respect to X, you get A. So you get transpose of this, and that's why I have A transpose times B. Okay? Now, if you simplify that and set it equal to 0, you get X to be A transpose A inverse times A transpose B, which is again the normal equation. This time much easier, normal equation. Okay? Now let's talk about the orthogonality principle.